Real quick, I'm Andy. I'm the CTO of Fairwinds. If you're here for Stevie, I apologize. She could not make it, so I have to give this talk. But I wanted to leave her on the slides because she helped me write a bunch of this. Stevie's fantastic, and this would be more fun if she was here. So I'm going to try to channel my inner Stevie and be exciting for all of you. Like I mentioned, I'm the CTO at Fairwinds. We do Kubernetes. We help people solve their Kubernetes problems. We run it for them. Long story short, we actually used to be a Rails hosting company like 10 years ago, and we managed so much of our customers' infrastructure that they were like, can you do more? And we were like, sure. And so they spun off an infrastructure company that became Fairwinds. And then we very quickly, about 10 years ago, settled on Kubernetes. So we've been working in Kubernetes since basically the beginning of Kubernetes. And that's all I'll say about our company. If you want to talk more about it, please hit me up later. You are here because you're interested, I'm guessing, in LLM Inference on Kubernetes. Just a quick poll of the room. Who here runs Kubernetes in production? Okay, about half of you. Cool. How many of you are using LLMs? Okay, in some fashion. And how many of you are running your own inference in Kubernetes or otherwise? Oh, one. That's surprising. Yeah. So I should preface this talk with, I'm going to focus specifically on running inference. I'm not going to talk about why you should do this because maybe you shouldn't. Frankly, there's a lot of good reasons not to, and a lot of places where you can get what I'm going to do here from someone else cheaper or easier or with a lot less work. This was very much an exercise in, can we, how will we, and what does it look like, and what can that give us? So I'm just going to focus on the how, and please don't worry about the why right now. So what is inference? Inference is basically running a model, right? And I'm going to simplify a lot of the AI terminology here because I'm not an AI expert. I'm an infrastructure expert. I'm here to talk about infrastructure, not the inner workings of how AI models work and all of that. I just want to show you how we get them running. But what we should understand about inference is that it is a little bit different than maybe a traditional workload that we might be running in our clusters. So there's 3 stages of an inference request. There's tokenization, there's prefill, there's decode. Each stage has different requirements in the hardware that it's utilizing, how it's using the underlying hardware. So some of them are CPU bound, some of them are compute intensive, some of them use memory, some of them use GPUs. So there's a lot more going on here than we would normally see with, I'm just running, a Go binary that I compiled that's, serving a static website maybe, which that's weird. I think only I do that. But the important thing here is that we have to understand there's a different mental model to running these things. So here's just a quick outline of that. Typical web workloads, generally CPU bound, not always, depends on what they're doing. They start up quick, they scale really fast, right? Especially if it's like a small binary. We often scale them on CPU. I would say you shouldn't. You should scale them on customer-facing factors like latency or request volume or things like that. But we can scale them on CPU. We often do because it's very easy to do in Kubernetes. And we swap pods in and out all the time, right? We expect a lot of pod churn with a traditional web application because those pods individually don't matter. They're storing their state somewhere else. They don't take long to come up. We can just throw them around willy-nilly all we want. Inference is a different beast. Inference requires GPUs. It's very heavy on compute. It utilizes the GPUs very heavily. GPUs aren't sliceable in most cases like CPUs are. So we divide up CPUs a lot in Kubernetes. We don't do that with GPUs. You can. It's kind of a newer thing. It's very complicated to do. I'm not going to show that today. Inference workloads start up really slow. So even if you have the model preloaded, like you're not downloading the thing. Downloading it takes forever. It's a large language model. It's big. But also, when you start up the model, it takes a large amount of time to get running. We're not going to scale these inference workloads the same. We're not going to scale them on CPU usage because they're using GPUs. But they can't also divide up the GPUs. So we're really going to scale on different factors like how many tokens can I process right now? How many requests do I have incoming to the inference server? How many requests do I have waiting from my inference system? So And then again, I think I've mentioned this a few times, but cold starts, just starting up from fresh, super duper slow. So you have to be a little bit careful with how you're running these things. So what do you need in your cluster to run inference? These things might look familiar because they're exactly the same things you need to run any other workload. You need to be able to schedule your workloads. In this case, we're going to need to be able to schedule them on nodes that match the resource requirements. So they have GPUs, generally is the requirement. We're going to need additional resources like GPUs and other things around that. We also need CPU and memory to assign to those containers. Generally, you're going to be GPU bound, and so you don't necessarily have to worry about how much CPU and memory you're running on those nodes, but you do still have to be aware of it. Networking requirements. If we're pulling models or we're moving a lot of data around in between those models, be conscious of the networking requirements of them. And then again, I talked about scaling signals, but we need to have metrics flowing related to our inference workloads to be able to scale on those signals. So I need to have more metrics, and we're going to show all this. The reason I'm talking quickly is I don't have a lot of time, but I have a lot of demo I want to do. And so we're going to get through this part real quick and get to the interesting part. Any questions before I get going? All right. Please feel free to raise your hand, shoot a question at me. I prefer to be interactive if I can. So what we have here is a Kubernetes cluster. It's called the cat box because it's where we put all of our crap. It's the dev cluster for a whole bunch of people at my company. So there's a lot of stuff running in here. There's a lot of different nodes running. We are using Carpenter to provision all of our workloads. So the first thing that I'll show is in the folder just above this one, our Carpenter node pool looks a little bit different potentially than your average Carpenter node pool might look. So specifically, I have a node pool dedicated to these workloads. And it has a few different instance types that are in it. I'm intentionally restricting them to specific generations and sizes because I'm only using a couple of these. And I did open it up to 24x larges. I try not to run those for too long because they're very expensive. But we have several GPU instance types. These are different accelerators on all of these. So we'll talk a little bit about how I'm going to utilize those in a minute. But we have different accelerator types and we have different sizes. Those are the primary things that we're going to see in here. I'm allowing spot or on demand because the availability of these instance types can be a little bit sketchy sometimes. So it's best to just kind of open up the pool. But if you're trying to keep it cheap and you're not worried about disruption, spot can be okay. And then I taint these with GPU node taint so that I'm not scheduling a whole bunch of other stuff on these right now. I probably could mix and match other workloads into here because I'm not utilizing all of the CPU and memory on these nodes. I'm really just using the GPUs. But since it is a test cluster and all of my coworkers are also using it, it's best to just kind of isolate this off for the purposes of the demo. So that's my Carpenter node pool. The other thing to note is that if you do want to run NVIDIA GPUs, BottleRocket and AWS have a very nice pre-built AMI, has all of the NVIDIA drivers already on it. Really just works straight out of the box. So this is the latest, or the version of Kubernetes that I'm using to the BottleRocket AMI. Makes it super easy to get it working. And then if you're not going to store your models off of your somewhere else in a shared storage somewhere or something like that, you're going to want to be mindful of your volume sizes. Because if you're pulling the language models into ephemeral storage, your pods can get really big and then you'll start blowing away ephemeral storage and then your nodes will fall over. So don't do that. Be cognizant of that. So that's the Carpenter configuration. Now I'm going to talk about two different ways you can run inference in Kubernetes. There's several different systems. We looked at probably 6 or 7 different for this particular talk. But there's lots of different, shall we call them, frameworks for running inference in Kubernetes. There's Kubre, there's VLLM, there's Ollama, there's KubeAI, there's Kserve, there's a whole bunch of them. In testing a lot of them, we came to kind of 2 that we liked for the demos because they're relatively straightforward to get up and running. One of them, we're going to start with Ollama. Ollama is your basic, simple, I want to test this out, I want to run a model on a GPU, and I want to play with some prompts. Ollama's super easy to get running in a cluster. So there's a Helm chart for this. It has, some configuration that you need to worry about. Let's focus specifically on enabling GPUs, because that's a thing that you're going to probably want unless you're running only CPU-based models. In this case, I wanted to run some of the larger models. And then I'm going to use NVIDIA GPUs. I'm going to tell it how to request those. All of this comes kind of default. The biggest thing that you have to pay attention to with Ollama, if you're testing it out, is pre-polling your models. So when you install this Helm chart, Ollama will go out and pre-poll any any number of models that you want, and pull them into the pod, and then it will also automatically be running those models. If you've ever run Ollama locally, you have to say like Ollama serve, whatever model. You can add more models. This runs exactly the same way. It's just wrapping it up in a nice Helm chart for you. So you'll want those working, and then obviously make sure that you can tolerate the taints. Use the node selector so that it selects GPUs, and then all I'm going to do is run a Helm upgrade install command to install Ollama in the cluster. So if I go to my Ollama namespace, what we'll see, I have a single pod. I started this last night because I didn't want to sit here and make you all wait for me to pull Qwen 3.6, 27 billion parameters. It's not exactly a small model. So that's running in the cluster. I also already have my port forwards running, so I'm just going to port forward directly to this pod. And we're going to go over here. I am running Pi less YOLO, which is Pi is an agent harness. It's a really lightweight one. It's the one that backs OpenClaw, so you've probably heard of it if you haven't used it. And I'm running that in a Docker container that's packaged up by this nice repo. So it's just running the agent harness. And then I have told it, actually we can, I have told it where to find the models. So because it's running in a Docker container, I'm actually coming back to my laptop here, pinning back to the laptop to talk to this. But I'm just telling it this model is available here. And so when we go to our Pi interface, where did I just put that? If we search for models, I can search for ones that are tagged Ollama here. I've already told it I have Qwen 3.6. And luckily, AI doesn't care about typos. And we can hopefully, if this is working, ask it something, and it will actually hit the model. That's assuming I got my IP address correct. Look at that. All right, so that's coming directly out of that pod running in my Kubernetes cluster. It would have taken you maybe 5 minutes to actually run the commands and another 15 to wait for it to pull the model, depending on which model you chose. So that's Ollama. Super simple, not a lot of configuration. Ollama can't do a lot of things. It can't split requests between GPUs. So if you're using multiple GPU model or multiple GPU instances, I believe it's kind of tied to one. There's just not as much configuration you can do with Ollama. It's not really built for doing multi-user inference. So this is where we're going to graduate to the other project that I have the demo for, and this is KubeAI. So if we go to the KubeAI folder in the same place, I have a lot more going on here. KubeAI is a full-blown controller. It runs in the cluster. It has a CRD associated with it called a model. When you tell it, I'm going to run this model, but there's a whole spec that goes with that model. So there's all kinds of configuration we can do. So the first thing we'll look at here is the values file. KubeAI can use Ollama under the hood, but it also primarily uses VLLM. So I'm going to use VLLM as the actual backend here. And I'm going to tell it all of these resource profiles. So now I'm going to say I have this style of GPU available. Here's how to use it. So here's all of the tolerations you need to use that particular GPU. Here's the node selectors that you need in order to use that specific accelerator or GPU. And so I have several of those in here. So these would coordinate very closely with my Carpenter node class. I would need those to match so that when these request nodes, they actually get them. So that's probably one of the more kind of fiddly pieces of this. The second bit is it'll do model caching. So I have an EFS file system that I've provisioned manual. I think there's a script in this repo, and I'll have a link to the repo at the end here if y'all want to try this stuff out. But the nice thing about Kube.ai being a full-blown controller is it'll manage the full life cycle of the model. So if I'm doing this pre-caching, as soon as I apply the model, it spins up a job that goes and pulls that model into the EFS cache. Now every node that spins up that wants to use that model, or every instance of that model that comes up that wants to use it, can pull it out of the EFS cache. It's a little bit quicker than pulling it straight from like Hugging Face every single time you start up. And then when you delete the model, it'll actually go in and delete it out of the cache. So it's relatively sophisticated in that way. The other thing that Kube.ai will do is auto scaling. So I can tell it, this model, I want, up to 15 replicas of this model running, and it will spin up new copies of it that will request new GPU nodes and add GPUs and take care of all that for me under the hood. So that's the values file for the Kube.ai chart. The biggest thing to note is those resource profiles. It's kind of the hardest thing to get working, and then the caching. I have a storage class associated with the EFS file system that I've put in the values file. It's referencing that. And then the big important thing is we have the actual model file. So this is where you get into the nitty-gritty details of how we're serving this model. So we're going to use the VLLM engine. We're going to use that dynamic EFS cache that I've already provisioned. This is where we're going to get it from. And then here's our min-max replicas, and then we've got ways to tune the auto-scaling. So we may not want to automatically just pull down a GPU node because all of a sudden there's no request. We might want to wait, a few minutes, maybe a few hours, maybe days before we actually tear that down, because it is hard to provision GPU resources sometimes. So then there's all of your VLLM arguments. And this is where we see the complexity of what VLLM can do. All of these things are tunable. They're all very specific to the model that you're running. I spent probably an obnoxious amount of time actually like making these 8 lines right here, interfacing with certain LLMs in order to do that, because there's a lot of complexity built into that right there that's tied directly to the model. So if you're an AI expert, you're probably sitting here laughing at me because I don't know all this stuff, but I'm an infrastructure guy. I'm finding values. This is what worked. The one that I definitely spent a lot of time working with is GPU memory utilization, because that can affect whether the model is actually able to start up without getting killed. So you have to kind of watch out for that as you're deploying these. So what this looks like is if I switch to the Kube.ai namespace, you'll see I already have a pod called model Qwen 3.6 running. I already have the Kube.ai pod running. What I'm going to do, just so you can kind of see how it works, is I'm going to apply this Qwen 2.5 model that I have. And you'll see it pops up a job pod that loads the cache. So that's going to sit there and spin for a while it pulls. And then once that's done, it'll spin up that model container, and you'll see that sit there for another 10-15 minutes while it starts up as well. So you can kind of see the cold start problem in action while I do the rest of the demo here. So the Qwen 3.6 model is running. The other nice thing about Kube.ai is it ships by default with this open web UI out of the box. So I don't have to configure my local Pi agent to talk to the model or do port forwards or anything like that. Like I am doing a port forward to the open web UI, but you can front that with an ingress controller or load balancer or something like that. So this is the web UI they give you. It will automatically pre-populate any of the models that you've installed in the cluster right here into this bar. So I want to talk to, well, I can't do 2.5 yet because it hasn't loaded, but 3.6, I can say, give me ideas for what to do with my kid's art. So you have this nice UI. It's kind of a UI that you're probably familiar with if you've interacted with any LLM. It stores your chats on the side. This UI can also be expanded to be multi-user, save sessions, be persistent. You can hook it up to a database. It'll do all of the things that you might want to do. So we're much closer to a full-fledged system that I could deliver to other people that they might want to use, rather than just kind of the toy in a box that I did with Olama. The other thing that we get out of the box with Kube.ai, which is super important, and we talked about this earlier, is metrics. So by default, it exposes a bunch of Prometheus metrics. I've installed a very short-lived Prometheus here. and you'll see we have a whole lot of VLLM stats available about how this model is operating, which means I can then connect this up to Grafana, and I can go back a couple hours so that we actually have things in here, and we can see how many requests do I have going at any given time, how many are waiting. So if I've got users that are just sitting there spinning, waiting to get their AI responses back, what's my token throughput, so I can start to optimize for that, how many tokens I'm pushing through the system at any given time, how long is it taking me to get my first token, right? How quick does it respond when I make that first question? How many requests am I serving? So all of these metrics can be used, to better inform you as the operator in running these models, but also inform better auto scaling. So now I can look at tuning how we spin up more GPUs or less GPUs going forward in order to serve my end users. And then we have end-to-end request latency as well. So there's quite a few metrics there. And then in addition to that, one thing that if you're pre-reserving GPU instances that you might care about is how well are we actually utilizing them. So very easy to install the NVIDIA DCGM exporter that does Prometheus metrics off of the NVIDIA GPUs. So now I have a full dashboard that tells me how many GPUs do I have, how well are they being used, how well is the GPU memory being used, how much power are they drawing, which if you're in a data center situation of your own, you might care. If you're running on AWS, maybe you don't. But we have all of these metrics available to us now that are similar but not the same to all the metrics we're already familiar with running web workloads in Kubernetes. So that's that. I really want this to load. There we go. All right, we've got Qwen 3.6 responding to us. It's not the fastest thing. I could probably change instance types and add a couple more GPUs and get it going a little faster. But if you run this same model on my M5 here, it's about quarter the speed of response running the 27 billion parameter model. So it's not a small model. It's pretty good though, I have to say, compared to some of the frontier models. It's really not bad. That's all I got. Oh, link to the repo. If you do want to try out any of this stuff, I do try to keep it up to date as I explore and test things and give this is the second time I've done this. So, yeah. All right. See y'all at happy hour.